All right, let's jump right into this. Welcome to today's Explainer, where we are taking a structural deep dive to look at exactly how we engineer the modern world to survive extreme winds. We're going to unpack the science, the math, and the sheer physical forces involved in wind load safety for engineers. So if you're an engineer, an architect, or honestly just someone fascinated by how our cities manage to defy nature and stay standing when the sky turns violent, well, you are definitely in the right place.
It is a massive, monumental question, isn't it? And it perfectly highlights the incredible stakes of modern engineering. Because we aren't just building for the storms we see on the news today, we are literally tasked with designing for catastrophic, worst-case scenario wind events that, mathematically speaking, might only occur once in 3 millennia. How do we even begin to quantify that kind of structural safety?
To pull this off, we rely on our foundational text, the ASCE 722 guide. This is our holy grail, our blueprint for mitigating these catastrophic hazards. This document represents decades of boundary layer wind tunnel testing, intense historical data analysis, and highly complex fluid mechanics, all distilled down into the critical provisions you need to keep people safe.
To make sense of all this dense information, we're going to follow a highly structured blueprint today. We'll hit 5 main areas: designing for the storm, the new tornado load provisions, updating factors and coefficients, the real danger of vortex shedding, and finally, knowing the standards limits. Let's get right into it.
Part 1. Designing for the storm. So the fundamental philosophy of the code isn't just about arbitrarily making a building stronger. The overarching goal is to provide designs that meet very precise target reliabilities based on site-specific climate data. To do this, the standard maps completely separate massive mean recurrence intervals directly to specific risk categories. It's a total replacement of the older, simpler concept of importance factors. You know, versions of the standard before 2010 used importance factors to artificially bump up design wind loads. But research showed that a single multiplier just didn't accurately reflect real variations in risk, especially across hurricane-prone regions. So now, if you are designing a critical facility, say a hospital, which is a risk category IV structure, you are calculating forces based on a wind speed with a 3,000-year mean recurrence interval.
Moving on to Part 2, new tornado load provisions. This is where things get really groundbreaking in the 2022 update, specifically with the brand new Chapter 32 aimed at mitigating tornado damage for risk category 3 and 4 structures. For the first time, tornado loads are intentionally separated from general wind loads. And why the separation? Well, we have to contrast a broad physical threat of a hurricane with the highly concentrated, devastating physics of a tornado strike. Straight-line winds from a hurricane impact a massive geographic area, but a tornado? It has a remarkably narrow path. Because of this, the basic design tornado speeds actually depend on the effective plan area of the building itself. Think about it. A facility with a sprawling footprint has a non-trivial, statistically greater probability of being struck by that narrow tornado path than a tiny building does. It requires an entirely unique set of calculations.
Historically, engineers pretty much agreed that tornadoes didn't dictate wind risks for intervals below 5,000 years, but a huge paradigm shift just happened. Recent in-depth analyses of tornado strike probabilities revealed that they absolutely drive the risks at the 1,700 and 3,000-year levels. In certain parts of the country, ignoring tornadoes at those lower intervals leaves critical structures dangerously vulnerable.
All right, Part 3, updating factors and coefficients. Let's move to the math and see how this standard updates the crucial variables you use every single day. Because ensuring wind load safety means the letters we plug into our equations have to accurately reflect the complex fluid dynamics happening outside. Take KD, the directionality factor. The crucial point here is that it hasn't vanished from your workflow. It just relocated it to give you far more precise control. In the past, it was lumped into the basic reference wind pressure calculation. By moving it over to chapters 27 through 30, the standard ensures you apply this modifier exactly where the directional nature of the wind interacts with the unique geometry of the building's main wind force resisting system. Now, if you're in the field, you immediately recognize GCP. When it comes to negative surface pressures on components and cladding, the code firmly locks the gust effect and pressure coefficient together. You can't just take a pressure coefficient and multiply it by some general gust factor when you're dealing with the powerful suction on the side or roof of a building.
And why are they locked together? Because, and this is absolutely crucial, you simply cannot separate the gust from the suction. Complex wake effects and separated flows around a building just don't correlate directly to a gust in the approaching wind. When wind hits a building, it separates at the corners, creating massive turbulence and shear layers. The suction ripping a panel off a wall isn't happening just because the wind blew a little harder for 3 seconds. It's happening because of the specific aerodynamic disturbance caused by the building itself. The standard demands you use that combined GCP value to accurately capture that localized peak negative pressure.
Which leads us perfectly into Part 4, the danger of vortex shedding. Designing for the wind isn't just about static head-on pushing forces. It's about the chaotic, rhythmic pulling forces of wake effects. Just picture the physics of it. As wind hits the face of a building, a bluff body, it can't neatly hug those sharp corners. The flow separates. A shear layer forms right next to the building, and the wind rolls up into a powerful vortex along the edge of the structure. Then, this vortex sheds off into the wake. And here's the terrifying part. They shed alternately from opposite sides. This alternating shedding creates a nearly sinusoidal crosswind force. The wind is blowing straight ahead, but the building is literally being yanked from side to side.
And here is the absolute worst-case scenario. If that shedding frequency locks into the first or second transverse modes of your structure, especially for tall or flexible buildings, boom, devastating resonance strikes. The intensity of this excitation skyrockets as a building gets taller and thinner. If you have an aspect ratio, so height to width, of 6 or more, you could be looking at crosswind vortex shedding forces that completely dwarf the standard head-on wind loads you originally calculated.
So, how do we practically apply these provisions to the complex, creative shapes modern architects love to dream up? Well, since the code is mostly based on rectangular wind tunnel tests from the 60s and 80s, engineers basically have to rationalize the shape. You either draw a giant rectangle around the whole thing to approximate it, or you break the complex shape into multiple rectangular sections, calculate the sectional loads, and combine them. It's a pragmatic workaround for a code that was, frankly, built on boxes.
Finally, Part 5. Knowing the standard's limits, because keeping buildings safe means recognizing that a code book is not a crystal ball. Expertly using ASCE 7-22 means understanding exactly what it cannot do.
As the authors explicitly state, this standard is ultimately a simplified analytical tool. Developing it involved trade-offs. The pressure coefficients are enveloping, meaning they capture the highest peak values regardless of wind direction, which realistically won't all happen simultaneously on a structure. It's highly conservative, yes, but it inherently lacks the nuance for estimating complex crosswind and torsorial excitations on wild architectures.
So, I want to leave you with this provocative thought. At what point does your target reliability demand you step away from the formulas and put a physical model straight into the wind tunnel? The boundary layer wind tunnel remains the absolute workhorse for the most accurate information on design wind loads. When you are dealing with extreme aspect ratios, low structural damping, or highly complex architectural forms, the simplified procedures of the standard simply aren't enough. Ensuring safety means knowing when to close the book and when to test the real physics. Thanks so much for joining me on this explainer, and keep building safe.